Fractal patterns may unravel the intelligence in next token prediction. Is next token prediction in language models simply word statistics? A recent paper attempts to answer it. A fractal is a geometric shape containing detailed structure at arbitrarily small scales, usually having a fractal dimension strictly exceeding the topological dimension. An object is called self-similar if it is invariant across scales, meaning its statistical or geometric properties stay consistent irrespective of the magnification applied to it. Language is self-similar with a fractal dimension of 1.4. It exhibits rich, similar details at all levels of granularity, from long scopes like documents to short ones like paragraphs. These details are equally important and equally difficult to predict, by self-similarity. Example of a process that is not self-similar, looking smoother at larger time scales. To succeed at predicting the next token, LLMs need to identify patterns at all granularity levels. But, learning patterns at large scopes is basically understanding the broad context and intent. Self-similarity formally shows why this is not a matter of simple word statistics. Self-similarity alone isn't enough for models to show intelligence. We need dependence. For example, Brownian motion is self-similar, however, with independent increments. That is, if we trust the market-efficient hypothesis, there is nothing to predict in the stock market. Self-similarity means that any dependence implies long-range dependence, intuition. A book can be summarized in paragraphs, i.e., self-similarity, so dependence in paragraphs, for example, its end depends on its beginning, implies long-range dependence in the document, for example, its end depends on its beginning. Long-range dependence is measured by the Hurst exponent, for example. In math, h equals 0.5, meaning no long-range dependence, but in GitHub h equals 0.8, meaning long-term coherence in code. Calculate fractal parameters with Palm 2L. A comparison of the fractal parameters across 8 different domains with more than 1,000 documents each in the pile benchmark. Math is markedly different because each document consists of questions, with no long-range dependence. A comparison of the estimated median fractal parameters by various LLMs over the entire pile validation split. Estimates are generally robust to the choice of the LLM. But the tiny variations in median H reflect improvements in the model quality. Downstream metric, indicated by bubble size, is plotted versus the median Hurst and the median BPB for all 12 language models. H turned out to be a good predictor of downstream performance, just like the perplexity-based bits per byte, BPB. But, there seems to be another pattern here. Improvements in BPB alone without impacting H don't always translate into downstream gains. Combine H with BPB to predict downstream performance. Take the average H plus 1 over BPB, here we invert BPB so that higher values are better. It works much better than perplexity-based BPB alone, especially in Big Bench Hard, BBH. Look forward to more work on fractal and long-range dependence for language models.